in Wilson. This is workshop number 4, and the name is theoretical modeling. Well, Ian will be explaining that it's more computational modeling. Okay, and the presenters, the people who will present in this workshop is Professor Woo-Chang Han from Yonsei University in South Korea, myself, Alfredo Juan, from Universidad del Sur in Argentina, Professor Ian Shuttleworth from the Milton Keynes Educational Trust, Milton Keynes, United Kingdom, and Professor Dr. Herbert Kubasek from Technical University Kaiserslautern. Sorry for my pronunciation, Herbert. It's good. In Germany. So I will just introduce this workshop, and then my colleagues will be one after the other in parts. Okay. Okay. This is supposed to be the program for the whole presentation. It is just not our intention to go for all over these subjects because we have no time, because it was an idea of having all the important things put in a sort of program. But we are not following exactly this program, but mostly. So don't worry if we jump from one subject to another subject. It's all organized, organized anyway. Okay, the emphasis in this workshop is the conceptual understanding, because you're an experimentalist. Our intention is not to make a theory, solid-state physics or solid-state chemistry, theoretically. It's just conceptual understanding of some important ideas and the understanding of the limits of simulations. Many times, an experimentalist has a problem and call a theoretician and said, okay, why to compute this thing with that size? And the theory people said, we can't, impossible. Anyway, so there are some limits of what you can simulate or what results you are getting. And the communication between these two worlds, experiment and theory, is essential to build a realistic model. How? Talking each other. We are trying to make a bridge of understanding, a bridge of languages from theory and from experiments, and to dialogue between these two worlds and understand each other. The workshop is mostly centered on DFT and molecular dynamics. This is not all the theory, of course, but just a taste of some methods. If you plot a word plot, you can see in all of these idea, understanding is the most cited. You see, this is a sort of idea. In the Stone Age, the people collect rocks, metals, whatever, something that is useful. Here, we go to the trial and error method. It is always experimental. And we have here, with all your machines, STM, scanning electron microscopy, X-ray machines, whatever. And many of us are here in a model. And what we need between these two worlds, we need, that's what we need. Wow. You know, we are here, this town is full of bridges. So this is our intention, to make a bridge between you and us, between theory and between experiments. Okay. And I just tell you where around this scale, electronic structure, molecular dynamics, Of course, simulation, you go to the scale of hours, you have continuum, finite elements, civil engineers, for example, doing this type of calculations. But we are mostly here. Herbert will be a little bit around here. Okay, now start. Ian will be starting with the fundamentals of density functional theory and calculations. Okay, thank you.
Well, thank you for that introduction, that build up. So I hope I contribute now to the bridge of our understanding. And what I'll do is I'll talk about, as we said, on the left-hand side of that diagram. So I'll talk about density functional theory. So this is a theory that kind of focuses right down just on the atomic scale. We're interested in small systems. So let's start. Okay, so let's be ambitious. We want to have a go at doing this sort of thing ourselves. So we'll start off ourselves. And what do we need in order to do density functional theory? So it's something you might have heard about, you might have heard other groups talking about it. What sort of things do we need to actually get started? So the first thing you need is an atomic structure, or at least you need some idea of what the atomic structure should be. You need a density functional theory package. I'll go through a few of the big players. There's a whole different types of the DFT package, and you need a computer. Okay, so starting with those tools, we can get a lot of really great, really useful information. You can get an idea of your surface structure, and you can get an idea of your surface functions. Right? You can also get some sort of insight into the electronic properties of your material, and as well, you can have a look at the magnetic properties. You can have a look then at vibrations, and you can also look at the optical properties. So it's a really, really useful tool. Okay? But we've got to use it with care. So what we're going to do today is we're going to take a little bit of an overview at the beginning into actually how the theory is structured, how it's formulated, what its limitations are, and then actually how you can get yourself in that driving seat and with a little bit of confidence start to at least think about using this technique. Okay? So let's talk about something that is possibly relatable to actually give you an idea of the theory and also why the theory exists and what the problems are in doing this type of calculation. I called it kind of relatable. This is something you've maybe seen either in grad school, either sort of maybe during like an M-level course or a final year QM course. You've maybe seen this example of the helium atom. And this idea that you've got two electrons, and to actually then describe the motion, the wave functions of those electrons, you formulate a Hamiltonian which has got a couple of terms. And you probably heard that actually this was then really, really tricky to actually solve. This was about the limit of the sort of thing that you could even vaguely attempt to try and solve either analytically or, really, really accurately. What does our Hamiltonian look like? We've got these two terms. So we've got two terms which describe the potential and kinetic energy of these two electrons. And then we've got an interaction term between the two electrons. So this maybe is ringing a few bells. And this is kind of the flavor of the sort of problem that we've got. Okay? Now, what we'll do is then we'll accelerate a bit. We'll think about, well, what happens when you get a system where there's lots and lots and lots of electrons? And this is exactly the problem that DFT was formulated to kind of solve. So now you can see you've got your ion cores there, you've got your electrons, and you can start to see you've got lots and lots of these interactions between electrons. Okay, so whereas in the previous example you just had two electrons, you've got one interaction between the pair. Now you've got loads and loads of them. And how quickly does this problem scale? If you start thinking about actually something that seems relatively innocuous, like a benzene molecule, 12 atoms, 42 electrons, the electronic problem itself, there's about 42 factorial permutations that you can take of that electronic wave function. Now, to give that a sort of length scale, if you kind of think of each of those permutations taking about a byte of space, you've actually got a computational problem and you try to solve it exactly, which is about 30 orders of magnitude bigger than the internet. Okay? So this is a really, really tricky problem to start solving, even for something relatively straightforward like internet. So we have to then think a little bit laterally about how we're going to solve this problem. And that's where DFT comes in. So first of all, let's put down our Hamiltonian. Like the Hamiltonian, we're on safe ground there. And actually then let's write it as it is for our problem without any approximations. And we can see we've got our kinetic energy term for our electrons. And we've got our electron and nuclear attraction terms. This is very similar to the formulation that you maybe are familiar with, the helium atom. And then we've got this electron-electron repulsion term. That's the thing that starts to cause all the problems. Okay? That's the thing where you really do get quite a phenomenal number of interactions. And that's where the problem itself becomes extremely challenging to solve. So, what we do is we then apply the magic of DFT. Now, we only have a certain amount of time in this workshop, and even just to start talking about how this came about, it's a wonderful subject, and it's really it's above the sort of things that we can actually do in this time. But what we will actually do is we'll actually then rephrase that many electron problem, and we will turn it into a question of electron density. So in a sense, what we're doing is we're just going to take all of these electron-electron interactions and we're going to, okay? So we're going to take all this complexity of the electron wave function that you saw on the previous slides that we talked about, the benzene example, and we're going to condense them and we're going to turn them into one electron density. Okay? We do that by using the Hockenberg-Kohn theorems. This is the magic key that unlocks density functional theory. And we turn this many electron problem into a single electron problem, which has to be solved many times. If you like to think in terms of pictures, I always do. I always try and draw, what do they say? A picture paints 1,000 words, right? So instead of thinking now of a problem like this, where you've got all of these interactions between electrons, what you've got is a single electron in kind of averaged background due to the other. If you like your numbers a little bit, you can think of this as an n electron problem being turned into n1 electron problems. Or if you like your numbers even more, this is the actual transformation that we're making, and we're turning a problem which has got 3n variables, where n is the number of electrons, into a formulation that has just got 3 variables, the average electron density. Okay? So that's the key that unlocks density functional theory. So let's use this, and let's now go back to our Hamiltonian. Let's see what effect this has had. So we've still got our electron kinetic energy and our nuclear electron potential energy and our electron-electron energy, but we are now able to solve this in a way where we're just treating it as a series of one electron problems. That makes life a lot more straightforward. We don't get something for nothing though, because our total energy now has got this thing here called an exchange correlation. Okay? So all the complexity of that electron wave function, we've averaged it. We haven't been able to completely get rid of it. Okay? It's all been condensed and it's been put into this exchange correlation. And there's the role. Okay? Because formally, the exchange correlation term, if we actually knew exactly the mathematical form it should have, formally, this theorem should work perfectly. The problem is we don't know the exact form of the exchange correlation. Okay? That's where we have to start using a little bit of judgment. That's where we have to, when we actually try to do density function theory, this is where you have to be careful. It's all to do with choosing the correct, the most appropriate form of exchange correlation. So if you guys are experimentalists, if you've ever spoken to theory teams about this sort of problem, the reason they don't immediately then give you all the structures and all the vibrational properties and all the optical properties that you want is because they're thinking about how do I formulate the exchange correlation function for this problem. Okay? So, how does that work? Now, there's a classic paper. It's a great one. Now, I'm hoping these notes or the video of these notes that we distributed, we've got some nice links here. And this is kind of what we call the, or what has been now called the Jacob's ladder of exchange correlation. Okay? So we start down here with what we call the local density approximation. This is the most common one. This was around 30 years ago, maybe. And this actually is the most straightforward approximation to this exchange correlation energy term, the one that you saw in the previous. Okay. It's good if you've got wave functions that are kind of localized. But what happens when you start getting things like metals? Okay. In that case, you need to make your exchange correlation a little bit more complicated. Now, for people who really like the maths, then you'll see that you've got this electron density term here. If you then go to the next level of complexity, so this is climbing Jacob's ladder, you actually have got your density, but you've also got the first derivative of density. If you think about things in terms of like Taylor theorem, if you remember that, so if you're approximating a function, you've got one term and then a second term, which is in terms of the derivatives. Okay, you can kind of think of it in that way. Okay, so we're building the complexity, we're making this sort of maybe more accurate. We're also doing it at a cost. In this game, you don't get something for nothing. Our cost here, if we start doing this type of calculation, is that it's computationally more expensive. Okay, what does that mean? It means we need a faster or a bigger computer, or we need to be more patient in waiting for our results. It takes longer to run. It gets a little bit more complicated. We can start using then what are called meta GGAs. These then become even more accurate, but you might notice here you've got another term. And for fans of things like Taylor series, you will notice, it's the next one in the series. This is the del squared term. Yeah. And we build on the complexity after that. All the time, we're making this more accurate, more reliable, but we're doing it at the expense of computation costs. Okay. Our next stage is hybrid. We have then what we call exact exchange. I mentioned this thing, exchange correlation. Exchange is like the Pauli principle. Yeah. So what we can do is actually we can throw an exact formulation of that into the calculation. Again, it adds to the computation expense, but it makes it a bit more reliable. Okay. And then there are other approximations, random phase approximations, and so on. We move up towards this goal of chemical accuracy, towards this goal where we're predicting things like energies or reaction energies to within maybe milli-electron volts accuracy. And that's the kind of thing that we're in. So that's a little bit about the actual tools. How does it work? And when you sit down and you actually try and you download a package and you start to actually unpack it and run it a few times and you look at some of the examples, or if you go and talk to the theory teams and they sort of try and explain some of their calculations to you and they start talking about self-consistent fields and what are they actually talking about? Okay, how does this thing actually run? Now, there's a very, very complicated diagram there, which okay, is actually then slightly blurred, but that's maybe a good thing because there's a lot of complexity there. We just want to take the overview from this. If you're real fans of this, I'll mention the package again later. It comes from the VAS manual, which is a very, very popular DFT package. But what actually happens then when you do a DFT calculation? When you set it running, your computer will sit there for what seems like eternity, and you will just keep looking at the output files and it will keep telling you iteration 1, iteration 2, iteration 3, and you were thinking, this is great, but what is it doing? Right, what it's doing is it starts with an initial guess of that lovely average electron density. Okay? And what it does then is it solves the Hamiltonian, the DFT Hamiltonian, using that initial guess of the electron density. That then generates a new estimate of the electron density. And what it then does is it compares this new charge density with the one it started with. And it says, is it changing a lot or has it become self-consistent? Okay. Is that new charge density really a lot different to the one I just had before? Or is it actually, has it reached convergence? Has it now settled down? Is it telling me what is new, what the averaged electron density is? Okay. If it is, then great. Your computer will stop running and it will say, fantastic. We've got now our density functional theory estimate of the charge density for that system. If not, it goes back and it starts again. It takes that initial guess, it adds a small increment, and it solves again the Hamiltonian. Okay? So that's the process that the machine is going through when you actually run it that very first time. So when you look at things like your output files, if you're wondering what's going on, that's what it's doing. It's actually getting a nice, converged, consistent value for that electron density. That density that we said earlier on is the magic, the key that unlocks DFT. What you do with that is you start with your structure. You will have solved your equation and got a value for your your and you then use that in order to get your observables, the interesting things that you want to look at, things like your energies, your optical properties, and all that good stuff that you actually set out about. All right. So that's then a bit of the background. Let's actually then look at a few of the applications. What are the sort of things it can tell you? First of all, you can get then the forces. You can take derivative of the energy with respect to the position, and you can get an estimate of force. You can use this for two things. First of all, if you start with structure, you're not quite sure what the structure should be, you'd let that structure relax, and you'd use this estimate of force to give you that relaxed structure. The second thing you can use it for is this kind of equation to give you some sort of estimate of the vibration. So that's then our first estimate. Let's actually think about using that, and we could actually think about doing a calculation. So we have two different types, two different approaches. Now, we actually then favor, in this kind of forum, we favor what we call the periodic structure. Okay, so this would be something, I don't know if you can see this too well, so this is actually a relatively innocuous benzene molecule sitting on platinum 111. And this is what we would call a periodic simulation. Now, DFT code itself is periodic, but you'll often see that some people are talking about just treating molecules in the gas phase. Okay, so that would be, you'd think about it, well, that's not really periodic, or it kind of is, but there's a few things around that that we'll have to think about. But more commonly, we would think about this sort of thing. So this is then the most typical kind of situation. You've got a nice surface here, and you've got a molecule sitting on the surface. You've got a periodic system, nice continuous surface, and for that, you would need a point sample. If you're actually then going to just look at a molecule that's in the gas phase, it's the same algorithm, it's the same code, then you would just use a much lower K-point sample. We'll come to actually what we mean by K-point sampling in just a minute. But this, as an experimentalist getting into this field, this is one of the key issues. So when you look at your code and you're looking at all the parameters that go into your code, one big thing you're going to look at is sampling. And you're going to be asking yourself, is this actually accurate? Okay. So, how do we think about this? You start, and you maybe again remember this, the block wave. Yeah, do you remember that kind of formulation? And the reason we actually then think about things in Fourier space is because DFT itself as a package spends a lot of time solving equations that look something like this, that are estimated in Fourier space. So a lot of the time, your algorithm is actually going to be working in K-space, and it's going to be solving this type of equation. Now, this type of equation on the right-hand side will contain these types of terms. So these are Fourier type terms that arise from the block theorem. Why the block theorem? Because we've got these nice periodic structures. Okay? And if you take a quick look at this, we've got two reciprocal space variables. We've got a K variable, and we've got a G and a G cutoff variable. Now, at this point, you're probably beginning to glaze over a bit and think, well, okay, what's this beginning to mean? Let's actually think about this in terms of a picture again, okay? To make it a little bit easier to conceptualize. What the DFT package is actually going to be doing is, here is your reciprocal space, here is your first Brillouin zone for the crystal, for the periodic structure that you put in. And actually what the algorithm is going to be doing is, for each point in this Brillouin zone, it's going to be solving an equation. Okay? It's going to be solving something based on these block terms, these block wave functions. So we've got two periods that we need to think about. We've got to think about how many K points in the Brillouin zone we're going to use in order to get a nice converged calculation. And then once we're at this, we're going to think about, are we actually estimating our wave function over a wide enough region in that Brillouin zone to get an accurate estimate of that wave function? How else can we think about this? What we do is we can think about, at each point in this Brillouin zone, we're trying to write down the block wave at that point in the Brillouin zone, which means that we've got to use a certain number of Fourier terms to describe that block wave accurately. You can maybe remember from Fourier theory, you've got to estimate up to a certain frequency to get a nice accurate representation of your function. And this is exactly what's going on here. So here you've got two periods that you need to think of. You've got the number of points in the Brillouin zone that you're going to use. And then once you're at this point, you've got the number of terms that you're going to use at that point to estimate the Brillouin. Okay. Now there's a lot of theory going in there. And what I want to do is I want to give you this concept because again, when you go and you look at a DFT package, you'll see a lot of parameters. And you'll be thinking to yourself, where did these parameters come from? These are a couple of them, and these are some of the most important ones that you'll find when you actually do a calculation. Because if you don't use enough K points, you won't get a very accurate calculation. If you don't use enough terms at each K point, again, you won't get a very accurate calculation. So, we'll come back to that complexity in a second, but let's just take a look at what a really just typical DFT calculation can tell you. So here we've got a nice equation of state for bulk platinum. Here we've got energies plotted as a function of the lattice constant. We can now imagine where the lattice constant came from. We're giving the DFT package a nice periodic structure. And if we actually plot these these energies as a function of the number of K points in the Brillouin zone, we can actually see that if we don't use too many, we get this kind of this wiggle. The energy hasn't really settled down. As we increase the number of K points in the Brillouin zone, you can see that the estimate of energy is becoming more and more consistent. So what we're seeing here is that we have to use a reasonably large number of K points in the Brillouin zone to get a nice, accurate value of the energy. Okay. What else do we actually use? Well, we're looking here, we've got three different types of exchange correlation functional. Okay. So this is just to give us a little bit of a flavor for this. This is something that we saw just a few minutes ago. So we've got our LDA, exchange correlation functional, and we've got two variations of GGA. And we can see here that comparing it to the experimental, experimental lattice constant, what you've got is as you've increased the complexity of your exchange correlation functional, you've got a nice converged lattice constant, which is actually pleasantly close to the experimental one. So is this all beginning to seem a little bit consistent? Are you now, even if you're not understanding the maths behind it, are you maybe now seeing the method that's in the balance? Why we do it like this? Okay. We've got then a little bit of help at hand because we have got a very complicated problem, and we've seen this thing, we have these things we call pseudo potentials. Where do these come from? And again, as soon as you look at a DFT package, as well as seeing K-point sampling and cutoff wavelengths, the other thing you'll see is pseudo potential. You'll be wondering, what on earth is it? If you take a look at a wave function from one atom, if you look quite close to the atom, you'll see lots and lots of oscillations in that wave function. Further away from the atom, you'll notice that the wave function becomes a lot smoother, settles down. We can actually then ignore a lot of this complexity. Why can we ignore it? Because normally chemical bonds occur at maybe an angstrom. So, okay, not at these sort of separations. So as a good approximation, we can actually get away with removing a lot of this complexity, kind of averaging it away. So we're getting rid of the core electrons. So there's a little bit of help at hand. There's a lot of resources for this kind of thing, and a lot of people are really enthusiastic. Your theory groups will do this, and they will go to a database, pseudo potentials, and they will download the pseudo potential of their choice. And more often than not, people will then try to, they'll use this and it will give them a lovely, pleasing result. You've got to test. As always, we've got to be careful. And what you have to do is every pseudo potential is generated assuming that your atoms have a certain electronic configuration. Okay? This isn't always the case. The electronic configuration can change, the bonding can change, the atom changes its environment. And if you actually then check some numbers here, you can actually see as you change your different valence states. So this is just a little simple example of silicon. As you change the valence state for silicon, you can actually see that the pseudo potentials, if you don't check them, you can actually get errors of a few electron volts in the energy levels of the valence states. Okay. So always worth checking your pseudo potentials. There's a lot more complexity after this. We get long distance interactions as well. So this is then another Jacob's ladder. These are then interactions which are not well described in DFT. These are interactions where there's not a direct chemical overlap. And all the time we're thinking about how can we accurately and efficiently include things in our calculation. I'm surely overwhelming by 5 more minutes. Okay. This is one point actually though, where it really is worth now turning to your experimental team. Think about the kind of substance you're looking at. Think about what is it that's actually making that thing hold together. A lot of people are interested in things like maybe graphene. Graphene has got a very strong van der Waals interaction, but van der Waals interactions themselves are kind of tricky to actually model. Okay. And you'll actually then see if you go to a literature and you kind of try and formulate it yourself, you actually see there's loads of estimations. And again, there's always this trade-off between accuracy and computation time. Now, at that point, just stop and have a think and really muse yourself. What's the best way to actually approach this? We're good. We're good.
You're done?
Yeah.
Okay.
I think so. I think
okay. Thank you, Ian. Okay. Please, if you have a question, you can put some right now. You can go question at the end. Whatever. Or in between. Don't worry. But Ian, on Herbert, myself, and Buchanan will all available, questioning everything you like and everything you want to answer and love. Are you working? Okay, I will continue with this presentation. I promise. Not a lot equations, more pictures. But anyway, there are some equations. Let's start thinking about a real problem. Maybe you are familiar with a picture like this. So I have here a sample of a catalyst, a supported platinum metal on maybe alumina. I don't know what this is. But this picture you are getting from a microscope used. Then you can think about this picture with this type of cluster of platinum atoms. And maybe you can think about this having 100 500, 1,000 atoms, whatever. But this picture can be reduced thinking that you have facets here, and you can choose one. Why you choose one? Because you have to choose many others, and then at the end, you get the best. Anyway, think about we are choosing 111, and you have in this ideal surface, you have many sides, the top sides, the bridge sides, and the hollow sides. And how do you simulate this method? Is using a sort of a two-dimensional infinite slab with some layers. How many you have to test, as Ian said? Okay, one layer, fast computation. It is a real surface? Well, you have to test using second, third, fourth layer, whatever. It is a matter of knowledge how many layers apply to your problem. If you use a few layers, you'll go faster, but maybe you are getting nothing good. Okay, after that, you have to compute the energy. Okay, you're getting using some of the packages Ian mentioned. Think about VASP, for example, or Quantum Espresso, which is free. And you are getting the energy of the whole system. You have to subtract, in this case, gold, which is one atom of gold on top of a platinum layer, and then you have to subtract the platinum layer. And then you can also simulate, for example, some oxygen on top of a surfaces, and some oxygen with different coverage and with different structures. How you get these structures in case of oxygen or ruthenium, an hexagonal phase? Well, you can do a low electron energy diffraction experiment, and you are getting this picture, for example, and then you can use another ordering on the surface. And then here you have to subtract, in this case, a half of an oxygen molecule. That's because we are looking at oxygen atoms. Okay, what happened after that? You have to enter in a process called geometry optimization. So in few words, program move everything. Okay, if you want to move everything, the cost, computational cost goes up. So you have to be very clear what have to move. Okay, in this case, you can relax the slab and you can relax the atom on the surface. You can relax everything if you want, but you pay a cost. Let's try to continue with some examples of some calculations, and just to give you a taste of what you can do here. This is a semiconductor, calcium oxide, and this is the slab we used some years ago. First things is just to check the results you are getting from calculations with experimental data. As Ian said, Ian made a comparison with the lattice parameter experimental. Here, we are making a comparison with LID. The LID experiments a 3% contraction of the layer, interlayer spacing. We're getting these 3.8 results in computation, which is very good. Never expect exact results, of course, but anyway, this is very good for the type of calculation we are doing. And then the next step is to try to absorb one molecule, ethanol molecule. How can be absorbed? Which is the geometry? You have to find the geometry, and you have to do a lot of calculation to find the right geometry. Here at the end, we found this sort of horizontal geometry, and we have this sort of vertical geometry. But in both cases, oxygen, hydrogen for the OH group, for the alcohol function, interact hydrogen with one oxygen of the surface, and the other oxygen from the molecule make an toxic bond with calcium. And the OH bonding is about 1 Armstrong. This is what you can get from the calculation. You can get the geometry. And in this case, we are getting this bond, which is relaxed a lot if we compare with the free ethanol molecule. This is about 1 Armstrong. We're getting here 1.5. And let's do what we have to do now. Check with experimental data. There was a journal many years ago from Professor Heides. He said ethanol dissociate heterolytically, this means broken, with an etoxide. Here this is the etoxide. And when hydrogen linked to a negatively charged surface is linked to the negative oxygen. So theory is matching the experiment. So that's the idea. Always we need to match the experiment. Let's think a little bit about bonding. This is just to remember. This is the picture of Lewis' idea of bonding. If you have 2 electrons overlapping, you have a bond. This is quite a simple idea. The pair of electrons as a bond. Then you have the hydrogen molecule, which is very simple. In a more sophisticated way of thinking, you have one s orbital and the other one s orbital interacting together, going to form a molecular orbital, and you have 2 options. You are getting this, which is the bonding orbital, or you are getting that, which is the anti-bonding orbital. Which is the magic here? You don't go here with electrons. If you go here, you are destroying any possible bond you are trying to form. So reason is you need bonding orbitals. And in other cases, bonding is different. It's ionic, like in sodium chloride. Anyway, this is some of the few equations, but just to remember, think about molecule population, think about we're getting this, the wave function. It is a mixture of 2 atomic functions with 2 coefficients. This is called local combination of atomic orbitals, LCAO theory. If you try to keep the square, well, the density, you're getting a term here, which is called the overlap integral, and which is related to overlap population, which is a parameter that tells you about the bonding. Of course, if you have an extended surface, not a molecule, just an extended surface, the concept is called crystal orbital overlap population, which is the overlap population multiplied by the density of state. It is a concept which works with solids, with surfaces. And of course, again, in the periodic system, you need this in a crystal, and the expansion of the overlap integral is made using the K space. And then I will show you one example. Here we was studying some iron slab, and we was studying what happened if we have a vacancy in the middle of this slab, and we try to get a hydrogen molecule inside this vacancy, filling this vacancy. And we get 3 possible situations. A hydrogen molecule in the middle of the vacancy, or 2 other locations. And let's talk a little bit about density of state. This is a sort of introduction. Remember, you have 2 hydrogen, and you're getting 1 bonding, 1 anti-bond. Think if you have 4, you're getting 4 and 4. Think about having 100, and you have 100 orbitals interacting, and you are getting this picture with more density. You have a dense state here and a dense state here. This is the beginning of the density of states. And let's see what happened. This is the band for iron, which is called the D band. And let's see if you have hydrogen. You have hydrogen here. This small peaks, this one belongs to hydrogen. You can do a projection on atoms, and you can do a projection on orbitals if you like. And using this, you can detect where in the density of the state plots are the projection of these atomic states or molecular states. In that case, we have a projection for hydrogen here, so it means that these two little peaks belong to hydrogen. Let's see what happened. This is the molecule put in the middle of the vacancy. And this is the plot for the crystal orbital overlap population. And this is the Fermi level. So it means all of these is filled with electrons. That means if you are filling the bonding state, almost feeling the anti-bonding state. Which is the meaning? The meaning that it's impossible to get a stable hydrogen molecule inside the vacancy. And where is then the hydrogen? Well, not here in the middle, it's in these other structures. And we check then what happened with the bonding with the metal. That's the key here. It's the bonding with the metal. And the other key is what happened with the metal-metal bond. Well, you are developing here a bonding with the metal. But at the same time, you are making a zone of destruction of iron-iron bond. So the metal bond became weaker. Why became weaker? Because the orbitals previously used in the perfect bond metal, this is you have this bond here, is lowering here. So because there are a lot of anti-bonding population and you are losing bonding between metals, which is related, this type of theoretical calculation. It is related to a quite relevant problem in metallurgy. When you add some parts per million of hydrogen on a steel, you produce a quite complicated problem, which is called embrittlement. So think about on a structure who have to support a lot of forces and put hydrogen to destroy this metal bond. That's the molecular interpretation of the phenomenon of embrittlement. Let's see what happened with this parameter overlap population. Start here with hydrogen molecule. It's 0.73, the distance, and the overlap population is 0.53. See what happened when it's interacting with iron. It's almost goes to zero. Why? Because the hydrogen-hydrogen bond is not there. And see what happened with iron-iron. This is the bonding where there's no hydrogen, or this is hydrogen in the middle of the vacancy. So 0.7 to 27 is the bonding. When you have hydrogen interacting close to iron, it goes down to almost 19. And of course, you can compute also the charge. In this problem, you are getting hydrogen charges negatively. And this again, another warning. Be careful. Be careful when you ask some theoreticians to compute the charge. Because I know people from electrochemist, people who is doing XPS, okay, tell me the balance state of the charge on a particular metal. Well, I can give you a charge. I am not sure what you are giving to you. Okay. It depends on the metal because the metal compute the density. And to get the charge, you need to make an integration. And it depends on the volume you choose to make an integration, it's the charge you are given. So don't trust a lot theoretician with compute charges. what you can trust is in the change of charge. This is a better idea. And of course, if you want to compute this type of overlap population, there is a program called Lobster that you can use added to BASP and getting this type of parameter, which is very useful to define bonding. Again, in another example, just to be, if you have here graphene and an atom of platinum going to graphene and hydrogen interacting with this, on a hydrogen molecule interacting with this, and you are getting here a picture where the flux of electron goes from the molecule to the metal, and from the metal back with a back donation to the molecule. If the back donation is enough and you are populating undibonded states, you broke the bonds in the molecule. This is well-known model in organic chemistry. It's called Cuba's interaction, and it's very useful also to compare things what's happening on the surface with organometallic chemistry, with some experimental data on atomic properties. This is a very good idea, just almost checking what these people from experiment and from other fields have to help you. Well, another parameter which is nice is called bond order. It's a very nice concept for Linus Pauling. It's just to calculate how many electrons, which is the difference of electrons in the bonding states and in anti-bonding states. And then just make a division by 2. And if these numbers are equal, like in helium-2, everybody knows that helium-2 is impossible. Why? Because you have 2 here and 2 here. So 2 minus 2 is 0. There is no 1. And there is again code here. Don't worry about getting all the names. The end, maybe we can get the PowerPoint to you if you want, which is also a code that compute the overlap and the bond numbers. Another example, again, graphene with defects. In this case, 1 vacancy, 2 vacancies, another vacancies, and substitution with bond. And you can compare what happened in one case or in another case if you put some rhodium atom on top of the graphene, in which is nice if you add graphene in a site where you get a vacancy, your binding energy goes up. Let's see these numbers. This here is one almost about 2 on a pristine graphene, but if you have defects, see this one, a single vacancy, you are getting 8. So it's multiplied by 4 of the binding energy is helping you. And what is nice about these calculations is you can compare the energy, the binding energy you are getting on a surface with the cohesion energy of the metal, which is rhodium. Which is the meaning? Cohesion energy is fine, 75. But the absorption energy, let's choose one, please, 8 or 7, is higher. Which is the meaning of the experimental? The meaning, if in this system you add rhodium, there's no cluster. Rhodium will be dispersed in case you're having vacancies within the mesh. And again, another thing which is nice, I like this picture. This is another tool available. This is they call electron density difference, which is the minus the density of graphene and minus the density of the original rhodium atoms, and you are getting this sort of picture. You can see here sort of electron distribution, which is nice. You can compare where are the distribution at the beginning, where are the distribution at the end. It's very quite informative. And now we're adding some hydrogen. And what you are getting? First, you are getting geometries, which is sometimes impossible to detect. Even if you have more sophisticated equipment, it is very difficult if you are dealing with hydrogen, because it's very difficult to see with equipment. So you can see here the bond distances between the hydrogen molecule and the interaction with rhodium, where rhodium is nearby a vacancy. Again, the bond order, remember which is the number for the bond order. You must get 1, because if you get 2 minus 0 over 2, 2 over 2 is 1. If you are getting 1 for the bonding order, so you're getting 1 for the bond order, you're getting a 1 bond. See what happened here. Hydrogen free, 1. It is okay. It's what everybody knows. You cut the electrons, the bond states. But see what happened here. Interacted with rhodium and rhodium interacting with graphene. This goes down a little bit, but it's goes down. Which is answering this? What do you believe? Is the hydrogen molecule broken or is just elongated? Well, my guess, it's a sort of elongation. And it's good compared with the numbers of after geometry optimization. You are not getting 0.78 Armstrong, you are getting about 1, which is still okay. The bond is not broken, it just elongated. And what is very important, because these systems are related to hydrogen accumulation and hydrogen storage. The next step of renewable energies is called hydrogen economy. There are still a lot of problems for the hydrogen storage. It's an unsolved problem. The theory can help the people who are making experiments. Another tool. This tool is called electron localization function. And this function provides a measure of the electron localization from a single determinate wave function made from Hartree Fock or from constant orbitals. This measures the extent spatial localization of the reference electrons and provides sort of a map where the electron pair is. I will show you a picture. This is a picture of the water molecule. See what you can see here, where the electron localization are, and you can see the density, where the electrons are, and where's the bonding are. This is the lone pair here. And it's a very useful tool. For example, here you have the localization of O2, absorbing on copper 100. You are getting here this with this gold color. We have a pink, you have a lot of electrons, and you have red, it has almost no electrons. It's a very powerful tool for describing the bonding on a surface. Again, using the density, you can go also in other way to study what is called non-covalent interaction, which is not simple. But anyway, with the density and with the electron localization function, you can also study dipole-dipole interactions, van der Waals interactions, pi-pi interaction, and also hydrophobic, hydrophilic, whatever. I don't have a lot of time to do that, but just to show you what can you study. You can study, for example, dopamine or nitrogen doped graphene here, and you can choose a way of mapping this electron density and describe this called non-covalent interaction. In this case, this is an amino acid, glycine. Again, on the surface, this is a nice problem related to censorship of building a sensor to detect amino acid in some samples. And again, coming back to density of states, remember, you have, for example, 2 lithium atoms, you are getting bonding and antibody, and if you have 4, you are getting more here, more here, and if you have a lot of both sides, at the end, you end with bonds. If you have a metal, these bonds overlap, and you have the Fermi level somewhere. If you have a semiconductor, you must get a gap. I will show you an example of a calculation where you are not getting a gap, so the calculation is wrong. And Ian, anticipate the problem. The problem is point sampling. Yeah, this is the idea of density of state. You have a high density of state. This is a sort of a linear hydrogen molecule. You have high density of state here, and you have high density state here on the top of the band. And okay, in case you have a molecule, you can also project the orbitals of this molecule, and you can get this picture. You have these pure orbitals with a molecule which is in the gas phase, but within the solid phase, this orbital here moves down. And all the orbitals which move down in energy means stabilization, means bonding. So you can choose projecting orbitals or projecting atoms. You can detect how the bonding is built on a surface. Let's try another type of calculation for comparison. In this example, you are checking out what happened with the density of a state that provides valuable information about the electronic structure of a material, including the distribution of energy levels and the nature of electronic states. For example, the peaks of the dot plot correspond to energy level with this high density of a state, indicating the presence of energy bands or localized states. You can see also in a dot plot if there is a gap, and you can correlate this with conductivity for other materials property. In that case, there is a comparison between the D band of platinum, which is a well-known precious metal, and this is a calculation which is performed with molybdenum carbide, which is a ceramic material. But see if we compare the bands. What do you see about this? What do you think about these bands? Well, they are similar. But in our case, you're using a precious metal, and in another case, you're using a quite cheap compound that is molybdenum carbide. So this is giving you an idea that you can change electrodes that is made of platinum. You can change with molybdenum carbide, getting the same, almost the same D band behavior. Again, taking a look at the bands with the density of state plots, you can see here the bands, which is white, for the bulk, a three-dimensional crystal. And see what happens if you compare with surface states. Surface state going here. So we are getting thin bands here representing surface states. This is the difference between a bulk calculation and a surface calculations. And you can also detect, okay, this band, which it belongs? Here belongs to S orbital. And this bands belongs to carbon P. This one here belongs also to molybdenum D. So this is a sort of a detective task, trying to see where in the density of a state there's one bond on another and where they come from. Well, again, the example of ethanol, this is the bond here, and you can detect the oxygen 2 bond, oxygen 2s, and calcium 3p. See what happened here. This is the Fermi level. So here, you are getting a gap. And that is okay because calcium oxide is a semiconductor. That is okay in this case. But be careful. Another problem with DFT calculation is the values of band gap. So it's a real, very difficult task for a theoretician to compute the exact value of a band gap in a semiconductor. So to be care of this, always you have to check with functional, with exchange correlation, with pseudo potential use, and all the parameters the theoretician use to get a number of Big Bang gap. Sometimes uses a sort of parameters, and you're getting a wrong, very wrong numbers. Here is some example of projections of molecular state. This is the molecular states. And when you project on an adsorbed state, you're getting broader ones, which means hybridizations. And if you go down in energy, lower in energy, it means stabilization. This is again other idea that you can get from theory. And I will show you one wrong result for a theoretician not well trained. And this is absolutely consistent with the idea of K-bond. You remember silicon. Everybody knows that silicon is a semiconductor with 1 electron volts with the band gap. So well-known experimental thing. See what happened with the calculation, DFT calculation, with this K-point mesh, 8 times 8 times 8. If you take a look of this, you can take a look here. There is no going to zero. There is no band gap. So with this sampling, you are getting that silicon is a conductor. That is wrong, of course. What you have to do, what Liam said, improve K-point sample. And with the right K-point sample, you are getting here the gap, and you are getting here the bands, valence bands, and the conduction band. Okay? So pay the price. If you pay some few K points, you are getting faster calculation, but you are getting wrong results. So this is sometimes colors, artifacts, and calculation. Again, this is also bad because this parameter with this used to fit the density of the state is wrong. You need to compare with the Heidegger K-point sampling, and you are getting right picture. Again, with this type of method, one is called VASP. I think we are mentioning VASP, but because we love VASP. Any other siesta. Siesta is another problem. Quantum espresso is another problem. Those are both free for one level. VASP is commercial, but it's a good program, became understandable. But anyway, you can get the band structure with a 3D solid. And here is an address for a YouTube movie, and you can go there and get it explaining how this plot is made. And okay, there's a little bit more. I have not a lot of time, but just to mention the last the last idea. The last idea is a method called elastic band. This is very useful, allows you to get activation energies on on a reaction path. Here you have hydrogen absorbed on cobalt. You have the initial state, the final state. This is a process which is spontaneous, but also you are getting here the activation. And this is called the transition state. You can do this doing calculation because transition states sometimes are so fast. There is no experimental method to compute what's happening here in the transition state. To measure what is happening. Well, calculation can help you with this method, which is quite powerful. Unfortunately, it's time consuming. Need a lot of computers or a lot of patience. Anyway, it's very useful. I will show you what happened in the old times when we don't use such type of tool. We just to study what happened with methanol on the top of a molybdenum carbide surface. And there is some experimental people from Hungary asking us what happened with this hydrogen. It is possible to broken this bond here, or this bond can be broken here. Okay, then we try to do some calculations, and just finishing. And this is our first results. This is how the energy goes in the moment hydrogen goes to the next hollow side. And we try to publish this. We submit to a journal, and the reviewers, one reviewer said, okay, this is strange. Okay, you are trying to make a dissociation and the energy goes up. And why stop here? Something is wrong there. So think about with some consideration with the reviewers. In that case, they make a good suggestions, and the suggestion was to elongate a little bit more this hydrogen, and we're getting here the activation energy. Sometimes calculations are not done in a full scale of the process. And in that case, you are not getting the good results. So this case, the review will help us a lot, and we are getting the activation energy. Today, you can do this in an easy way using NET, which is the method I mentioned. Just to finish, I'd like to say thank you for your attention, and thank you for all of the people of my group who helped me to make this PowerPoint. And I hope you get a nice idea of what you can do regarding bonding and density of states, overlap population, and bond order when a molecule absorber on a surface, and the interaction and the relationship with experiments. Thank you.
If there are any questions? Any questions?
Good. At the end.
Maybe then. We will now switch the topic quite drastically. No more electrons, almost no electrons. I will talk about molecular dynamics. And this, I will make a few points about the basics. So what can go wrong if you use molecular dynamics? And then I will try to give some examples to show you what kind of understanding we can gain from the method of molecular dynamics. Molecular dynamics is very simple. The idea is you just solve Newton's equations for a big system of atoms. Newton, this is classical mechanics. The first to think, can we use classical mechanics? Yes, we will do it. So I will only show you cases where this is possible. But of course, this question arises. So if you do proton transport in water, for instance, it's not good. But for many other occasions, it will be good. Many atoms means in the order of millions of atoms. This is the distinction to what we saw before. DFT is more like 1,000 atoms, and it's difficult to handle more than 1,000 atoms. And with molecular dynamics, immediate atoms is standard. So you can put it into one core. So if you have a desktop computer, 1 million atoms is fine. If you want to do 100 million of atoms, I will show some examples, you need a big cluster. But with 1 million atoms, you can do it at home, you can do it at your desktop computer. We did not see time scales up to now, but if you do DFT, time scales will be of the order of picoseconds. With molecular dynamics, you can go on longer time scales. So 1 nanosecond is typical. But again, I will show examples where you can go to 1 microsecond, and this may be the limit nowadays. So if you want to go beyond 1 microsecond, which is important for many applications, MD is not enough. You have to go to use other tools. But for quite a number of things, reactions going on, or conformation changes in large molecules, a microsecond is already good enough. Spatial scale, well, if you have 1 million atoms, maybe your scale will be 10 nanometers. If you go to hundreds of millions of atoms, you go to 100 nanometers. So this is sort of scale that you can handle, and you can say that it's quite big already, at least for atomic simulations. Okay, this is also important. Like 30 years ago, every student had to write his own code for molecular dynamics. The code is not difficult, it's 100 lines, so every student can do that. Nowadays, this is not necessary. We have very good MD engines. I want to mention LAMPS here. This is freeware, so you can just download it and use it. So everyone, every experimenter has the possibility to use it. And this is actually what happens. So you just take it, there's a good manual, you use it. But as I said, there's some pitfalls, and I want to describe some pitfalls. There's also other MD engines. LAMPS is used mainly for material science, or often in the material science context. NAMD, for instance, and GROMACS are more used in the bio context. I said it's very simple. Indeed, the idea is very simple. You just solve Newton's equations. The problem is the right-hand side here. What are the forces? When Newton wrote down this equation, he thought of the gravitational force between planets. Let's say this is well understood. Later, we had Coulomb forces, electrostatic forces, also well understood. But now we want to use forces between atoms. What are the forces between atoms? And we have to think about that. First, you might think that's very simple. This is such a generic potential that you might have. I mean, there should be attraction when two atoms come closer together. But when you push the atoms too close together, they will get repelled again. So you get a sort of universal curve, which is always true. You have one minimum, which is the bonding distance between two atoms, and we have to exert some force to separate them, or if you want to press them further together. This is a binary force. It's like gravitation, like here. So it acts between two particles. And if there are other atoms around, this potential will not change. And this simple idea has been used in the start of molecular dynamics. This means like 60 years ago, and the Lennard-Jones potential is a good example of that. Later, people wanted to also to study chemistry, and they said, well, with such a binary potential, we can just study vibrations between two atoms. That's not yet chemistry. We also have to include bond bending forces, and torsional forces means four-body forces. And there's now many force fields available. These are called force fields for some strange reasons. Strange reason because of potential energy. It's not a force. But the data behind all these force fields are available for many, many systems. They have been built up in big databases, and they are, in many cases, trustworthy. What about solids? I want to show you now that the idea of having two-body forces is not good enough to describe solids or actually any chemistry that is going on. And I want to do this with a simple example. Let's first take two copper atoms, and then later we want to insert a third copper atom. So the question is, what is the force between two copper atoms? And for copper, we assume there's this configuration, so a filled 3D shell and one electron in the 4s shell. So if you have two copper atoms, they will form a covalent bond because each of these copper atoms gives away one electron to form the bond. Easy, yeah. Now, if you push a third copper atom in between these two, this means you want to have a copper trimer. Does the interaction change? Yes, it changes dramatically because this copper atom also has one electron. It wants to introduce this electron to the system. This basically means it will destroy the strong bond between these copper atoms and will establish its own bond with all these three atoms. This means the bonding between, or the interaction between two atoms changes dramatically if a third atom comes in. This is called many-body forces, because you cannot describe the interaction between metals, between metal atoms, by pairwise interaction. If a third partner comes, it wants to be part of the game, it wants to share its electrons, so it wants to share also in the interaction. And this means since now 40 years, we know how to do this. We know how to describe metals, metallic bonds, and also other bonds. And this is done with the concept of many-body forces. The famous example is the embedded atom scheme, which is used for metals. So you have for the potential energy of the entire system, you have pair forces, which basically describe the repulsion of atoms when they come too close. But you also have a many-body term which describes the interaction of each atom with the electron gas which is around in the metal. Okay. So this means now since 40 years or so we have, let's say, valid or reliable potentials for large classes of materials, also for metals. If you now look into which potential to choose for your problem, let's take an example. Let's look at iron. Iron is an important metal. If you want to describe an iron surface, so you go to one of these repositories where you find which potentials are available, and it shows you now there are 23 potentials in this repository. I mean, there are more around, but they are not filled. They did not yet go into this repository. This is the repository built by NIST, the American Institute of Standards, but this is the repository used for lamps, so they are all available for lamps. You can just choose what you want. And then which potential to choose. All these potentials have been designed, or each potential has been designed with a particular application in mind. So some are good for melting, others are good for surface properties, others are good for plastic properties. You have to think of what is your problem, which properties should be represented best in your potential. One example is here, Mendeleev. It's an often used potential for iron. And Mendeleev is a potential builder. He has built many potentials. He says this potential here is in agreement with lattice parameters, elastic constants, and blah, blah, blah. You can read for what it has been made. And for instance, here you see no surface properties. So if you want to use this for surface properties, first you have to make sure have the surface properties been already studied with this potential? Is it a good potential to use or not? So this is to make you aware there is so many potentials available. One has to first look which potential to use. This is a slide from 2012, so already 10 years ago, but still it's very fine. It's a time scale from 1980 until, well, 10 years ago. And then you see the computational cost per atom, per time step for these potentials. Leonard Jones is somewhere down here. Yeah, it's not even mentioned. Yeah, very old. These are these embedded atom models for metals that have been used, and many other potentials like charm. These chemical potentials that I introduced to you are here. But you see now in the later times, many more potentials have been built. Basically, they are more costly. So actually, many studies are still done with these older potentials. But I want to remind you, if you have a particular problem in surface science, maybe it's good to choose one of the newer potentials because they are optimized for the application that you have in your mind. I will come back to these react potentials for use in chemistry a little bit later. An issue of size, I told you 1 million atoms standard. This is now a simulation with many hundreds of millions of atoms done on a supercomputer, so I think in Lawrence Livermore, and for 1 microsecond. This is a particular application where they look at compression of a metal. It's under high strain. I think the strain was here 50% compressive strain. They wanted to look what happens. And it's just to show you that you would not see such complicated, complex defect structures building up in such a material if you use a smaller sample. So sometimes it's really important to go to large samples to do your business. But often it's not so relevant. And then what you do is you take a smaller sample and you build a boundary around your sample. Okay, in this case, of course, there was also a boundary, like out here, but you could say what happens in the inside here should not be affected much by the boundary, so you can trust it. But if you have a small sample and build a boundary, you have to think about which boundary to use. Often you will use periodic boundaries. Sometimes you use free boundaries. And this is just an example to show you that it really does matter which boundary to use. This is now an indentation simulation. Oops. And so what you do is you have an indenter at the top of the surface. You just see here the indentation process. And this is dislocations that are emitted down into the solid because of the high pressure exerted by the indenter. And you have a fixed boundary surface at the bottom surface. What happens is the dislocations will be repelled from the bottom, so they stay inside the material. If you have a free bottom, they will just be absorbed. It's a boundary. This is just to make you aware boundary conditions matter. Usually you do have to have some conditions at the boundary because you cannot afford 200 million atom simulations. You use boundaries, but this is a warning. Be careful. Think about what you do. Another issue is thermostats. If you do classical mechanics with your atoms, the total energy is conserved. Total energy means the sum of potential energy and kinetic energy. But in many applications, you want to conserve temperature. So you do not want to conserve the total energy, but you want to conserve kinetic energy, because temperature is kinetic energy. And this means then that you do no longer solve Newton's equations. You will solve something different. But in these packages, there is some buttons that you push, and then you have a thermostat. So it does work, but you have to be careful. I often get papers to read or to review who do non-equilibrium simulations with a thermostat. And then you think, what does this mean? I mean, this is non-equilibrium simulation, a non-equilibrium condition, but there is a thermostat. So there is a daemon inside that fixes the kinetic energy. This is not realistic any longer. You cannot believe such simulations. Yeah. So this is just a warning. If you use a thermostat, make sure it's for a thermal equilibrium simulation, because then it can be justified. But if it's not in thermal equilibrium, it may give rise to artifacts. Statistics, okay. Okay, this is about chaos now. Often you make one simulation and believe this is the result. But actually classical mechanics is more complex. In classical mechanics, we have chaos. This means the definition of chaos is if you change your initial conditions a little bit, the result of your simulation may be very different. What means changing your initial condition? It means you start with a different time. For instance, because then thermal agitation in your material will be different. This is the famous example for chaos. It's chaos in a 5-body system. It's the sun and the 5 innermost planets, and this is chaotic. And so in classical mechanics, chaos is quite something that we have to live with. And this is one example, and this is a friction simulation. So here's a substrate, some sample. It's iron, I think. We take the indenter, we indent it, then we scratch on the surface, then we reduce the indenter, and we measure the friction coefficient. That's a simple friction experiment. And now this is the friction coefficient versus time. It's this time while we do this friction experiment. And we just look at the dry data because there's also data for, there is a lubricating fluid inside. We just look at the black data. And what we see here is we have a wide band, the band between these two lines of results, because we repeated the simulation 8 times. So it's 8 replicas. Nothing is changed. It's the same material. Everything's the same indentation point. We just started a little bit later. So the thermal agitation of the material, this was at 300 Kelvin, the thermal agitation was a little bit different. And you see the average friction coefficient, of course, is the same. But at any instant, you get quite different results from the simulation simply because the atomic positions are a little bit different. This is just a warning that be careful, make statistics, make sure that your results are really reliable, that they are representative of what is going on. If you just do just one simulation, maybe it's an outlier. Okay, so this was about the basic, some facts for people who do not make molecular dynamics every day, just to make you aware of which problems may exist. Okay, the first issue now I want to go into is reactions, chemical reactions. And I said there is now, maybe 20 years ago, they started a new class of interatomic potentials called reacts, like reactive potentials, and they allow to do reactions between atoms. This is from an overview by this guy, Van Loen. He invented and developed this class of materials, potentials, and he's still working on this. So all these potentials are connected to his name. And this is from an overview written some years ago. For the green atoms, for the green elements, the potential is available, or was available at that time. I will not go into details, it just means it's complicated. Yeah? I will not go into details. This is how he makes sure that things are okay. He compares here the carbon-oxygen bond dissociation energy for some molecules. The molecules are listed here. Quantum mechanics, so to say, computational chemistry based on quantum mechanics, and this classical mechanics simulations based on this reactive force field. It just compares what is the bond dissociation energy and the energy of the potential energy with distance, and he makes sure seems to be okay. So the potentials are verified in such a way. Also for the charges, he compares the charges. You have to calculate the charge somehow, and this Rex potential does calculate the charge every time step. So he has a scheme how to do that. But again, he compares with DFT. No, I just learned, never believe DFT. Okay, but still, it's quite okay. Yeah. Rex development tree. This is because Rex, he emphasizes Rex because for this community here, surface science, Rex may be really the big good potential for you because you can do reactions on surfaces with it. There is two main branches. One is oxygen, so because it's a combustion branch. So what happens if you add oxygen to a system consisting of carbon, hydrogen, or things? And the other is the aqueous branch. So what happens if you have a surface and water above it? Good. Biology, I mean, there's also quite a few applications in surface science with large proteins on the surface. This is well handled by schemes like ROMAX. It's an example for a large molecule. You can do adsorption simulations on that. The problem is there usually the time scale. The spatial scale is okay. So all of this fits nicely into this 1 billion scheme that I told you that's okay for a desktop computer, but the time scale is a problem. So usually if you send such simulations, okay, what you want to do is have a protein, it just goes down to a surface and you want to see what is the conformation change, what will be the conformation on the surface, and so on. This may take a long time. So some journals just send it back to you and tell you, you did not wait for 1 microsecond, I will not give you a result. So here time scale is really the issue that you have to consider. It's the same thing. This is again from, it's a surface problem, but now it's only soft matter that we see here. We have here a receptor. It's a receptor in a human cell, an NMDA receptor. This is the lipid membrane in a human cell. So you have water in the extracellular region, we have water in the intracellular region. This receptor, and then I think this is filled with probably with ethanol, so it's ethanol molecules. So this is about the interaction of ethanol with the biological system. This is possible nowadays. Again, time scale, here is the problem. This means you have to stabilize this lipid membrane, and this means you have to wait 1 microsecond basically in order to show it, yes, it is stable. So the advantage of what you get from such simulation is that you may find out where the alcohol molecules are actually going in. So these are the alcohol molecules, and they will bind to some special places, which are shown here in this receptor. And in this particular study, then, this was the computation indication for what is going to happen. And later they did experiments on mice in order to show that this really is valid. So this is nice. Such big simulations can help you not only in understanding what is going on in such interface systems, but it can also be instructive for later experiments. This is another example with reacts. Now we take a DNA. This is part of a DNA molecule that we see here. And we look at the interaction with ionizing radiation. So here is an ion which ionizes and gives energy to the water and also to the DNA molecule. This is now a tiny simulation. It just has something like 100,000 water atoms inside, and also simulation time is small. But what you can get from such simulations is you can see where actually bond breaking may happen. So here you see an overlay over the initial and the final state, it means broken state of the DNA. And you see at this point, you had the splitting of one of these helices in the DNA. Another example of the use of molecular dynamics is phase transformations. Often you study the phase transformation from solid to liquid, so like the melting transition, or you study amorphization. This is easier to do. What is more difficult to do is to study real solid-solid phase transformations. The prime example here might be iron. This is the phase diagram of iron. You have temperature, you have the pressure. At small pressures and temperatures, iron is in a BCC state. If you heat it up, it will become FCC. If you put pressure on it, you get an HCP phase. But this looks very simple, like it's an element. Yeah, it has been known for more than 100 years. There is no potential available in MD that predicts all of this. No potential. I told you 20-something potentials alone in this database. I think in total it will be 40 potentials. None of them can predict this. But what is possible is there's potential that predict this transition or this transition, maybe also this transition. So you really have to tailor your potential in order to describe the particular transition that you are interested in. And this, of course, also applies to all other phase transformations that one might want to study. First, you have to make a potential that describes this transformation. So out of these 20 or so potentials, there's only 1 or 2 or 3 that describe the BCC FCC phase transformation under temperature. And I will now focus here on the so-called Mayer-Intel potential, which has been developed 25 years ago. Okay? And this is now the free energy of the two phases, BCC phase and FCC phase, as a function of temperature. And you see they cross here somewhere at 500 Kelvin. Reality, unfortunately, is at 1000 Kelvin. As I told you, no potential available that does it, but at least this potential does have a phase transformation at a small temperature, but we can always say we make some simulations and then we scale our temperature to experimental temperatures. We make our simulations to get some insight into the atomistic dynamics of such a transformation. Okay, since you cannot see here very well the transition, here's the difference between the free energy of BCC and FCC phase is shown as a function of temperature. Here's the 0, and you see the experiment is the black data here, and the Mayer-Intel potential is the blue data. And there's many, many others, 20 other potentials that do not feature this transformation at all. So what can you do? You can, for instance, study the interface. Now, I do not show here dynamics. It's just the interface between the BCC phase and the FCC phase. And on the right-hand side, you see some high-resolution TEM measurements of how such an interface looks like. And this would be what one can see in the simulation data, a very complex interface. This is here colored by the potential energy. You see the interface is really not homogeneous, similar to what you can see here. and they're threading misfit dislocations reaching out from the interface to one of the faces. Oh, this is another nice thing. You can make an indentation, so this means this transformation we talk about is temperature induced, but now we can also see what happens if you put additional pressure on it. So we do an indentation at some temperatures, like if 500 Kelvin, you start with a metastable phase. This means you start with FCC, and you can see how the pressure starts, induces the transformation, even though without temperature it will not happen. Okay. About defect recognition. This is a major topic. I told you, usually you use 1 million atoms, and then you have the data of 1 million atoms at each time step. So you get 1 terabyte of data, but you are not interested in all of this, want to throw it away. You're just interested in some special features. For instance, you want to know, are there some defects? The ordinary crystal structure is not interesting, but the defects are interesting. Or in this case, you would like to analyze what is the local lattice structure. We start with FCC. Do we get some local BCC or HCP or whatever reasons? What happens if you do a transformation on the close to the surface by light, by any external induction? How do you measure what is the local structure? It turns out it's not easy. I think I will not show it. But people, of course, thought about this now for 20 years. The good news is that many of these ideas are now available. There's this tool Ovito. It goes with lamps. So if you use lamps, usually you do data analysis and graphical representation with Ovito. It used to be cost-free, but now this guy, he has a company now. Yeah. He left university, he built a company. So there's still some sort of raw version that can be used free, and this is what we have. But if you want to do some better analysis, Python, write your own scripts, you have to buy it. So this is now an example of what is possible to do. This is now a complicated example, so we take a nanofoam. So it's a porous structure, 50% foam, 50% voids, 50% material. And also we take a complex alloy structure. It's a high entropy alloy. So it's complex both from the point of view of atomistic composition and of geometric structure. But this is what is interesting now, yeah? So you look at this, and then many of these standard tools that have been developed in the years before do not give you sufficient results. So what has arisen now is you try to apply machine learning on such geometries. And this is now an example which, to the honor of our chairman, is taken from Argentina. Yeah, and he wrote a tool that allows to find more defects in your complex structure. This just means in the 1 terabyte of data that you get, it's really hard to find the information that is interesting, but there exist tools that are freely, more or less freely available to do so. But sometimes even then, nowadays, if you have some new applications or some complicated materials, you have to invest some brain in order to get more results. I think I will not go too much into detail here. An important question often is how to find dislocations. This means line defects in the material. I think I will not stress this too much. Maybe some words about topological systems, because this is now really surface science. There's a recent paper here from Ma. So you have basically iron at the 2 sides of the system, but the iron is oxidized because iron usually is oxidized close to the surface. So you take your iron oxide, and in between you have some sort of lubricant. So it's an organic glycerol or ethylene glycol mixture. We experimented with different lubricants in order to find out what happens here. And then he does a sliding simulation. So he keeps the bottom rigid, but he moves the top towards the right-hand side. And then he has a thermostat. Okay, I warned you about the thermostat. The thermostat is not everywhere. The thermostat is just here at the outside to absorb some excess energy. There's not a thermostat everywhere. The thermostat everywhere would be not so realistic. And then this is energy conservation here. And then he just watches what happens. And because he uses reacts, he can see how this glycerol decomposes, and out of the decomposition products, water is formed. This is the result of this study. And it's just an example to show what can be done nowadays with reactive potentials in situations that are important for surface science. This is another example. Maybe I should stress also this. The interesting, again, we have an organic lubricant here, but now we have amorphous carbon sheets here. The interesting thing is that these were not classical molecular dynamics simulations, these were quantum simulations. So it's basically DFT, what we saw before, but you do it on for each time step, you do a new DFT. We saw how you get forces out of DFT, use these forces to go further on in time. This is possible for, let's say, a few tenths of 2 per second. And this will be my final topic, role of electrons. In some problems, electrons are inevitable. We need electrons, but electrons have no place in molecular dynamics. Yeah? Molecular dynamics is about atoms. Electrons would have time scales because they are so light, have not such a light weight. They move on time scales which are much faster than the electrons, and then they are quantum. Electrons are quantum. What can you do? Yeah. You cannot do classical mechanics with electrons. But I want to show you 3 examples what you can do with electrons still, or how you can handle electrons in MD. One example is, this is now UV laser irradiation of a lithium fluoride thin film. Lithium fluoride is an insulator with large band gap, but if you have UV laser irradiation, it may excite electrons from the valence band to the conduction band, and this may break bonds, and then you may get some results in the atomistic motion. This is shown here. So if you have only a small irradiation, nothing happens. At high irradiation, we get melting in the material. At still higher irradiation, we get multiple sporulation of the material. How can you do this? So how can you excite the electrons with the laser beam? That's easy. But how do the electrons then convey the energy to atoms? You cannot do this directly in MD. You have to write your own equations for the electron kinetics, so to say plasma physics, and you have to solve the plasma physics equations separately or in addition to what you do with the molecular dynamics simulation. So again, you have to build up your, skip that. This is another example. It's a very prominent system. You have quartz and water interface, but now you want to study it under varying pH values. And pH is a concept that is not, 1 minute. pH is a concept that is not directly inside ND. What you do is you change the surface charge on your quartz in a well-defined way. And this then mimics the effect of a higher pH in the water. And I think that's it. That's the conclusions. We have larger time scales and space scales than with quantum methods, but one has to be careful in a number of things, basically with force fields. These were my 30 minutes.
Okay, thank you.
Okay, thank you. The questions either now or later. Yeah.
I have a quick question.
Yep.
you showed this example for iron actually, where it was very difficult to find the right potential. And why was it so complicated for iron? I mean, what was the reason that like the potential could not be found, which could predict these phase transitions in iron?
Okay, the potential was found or was made actually 25 years ago, exactly to study this phase transformation. So phase one, there's also two other ones, but we made also simulations with the other ones, and they show the wrong kinetics. So it's not good. So even if you have found a potential, it still may not be
The right.
good enough to do.
Okay. Magnetism, I know. I did some finite temperature simulations, including magnetic effect of magnetism, magnet phonon coupling, and then basically got the right transition temperature. Okay.
Iron also very strange electronic things. But this is only stable because of ionic vibration and entropy in 0 Kelvin as well. Oh, the first. Okay, thanks very much for your patience. I would be the last speaker, right?
Yeah.
Okay, I don't want to use any equation in my slide. I'm gonna beat Alfred. But I'm gonna talk mostly in terms of materials design. I'm not gonna go details or DFT calculations. Yeah. Keynote, please. This one, yeah. Can you? This is PDF or keynote? PDF. No, I need a keynote. I told you many times.
Yes.
Yeah. Who's calling? Okay, go to first slide first. Page number 1. Are you student? Okay, this is my slide. Okay, my topic is this section, but I'm going to talk about artificial intelligence, AI, and machine learning method, especially on the material science point of view. So this is my order of the speaking. The first one, I'm going to say the classical theory and modeling basically is law. It's thermodynamic kinetic laws. Law is very different from principle. This law is the summarized something rules from our daily experience. Basically here, thermodynamics and kinetics in classical term. But first principle we cannot derive. It is obvious from our intuition or visions. First calculations came up, we say principles. Why this principle came up after the laws? Obviously, there is a limitation by laws to understand design materials. And nowadays, even we don't care about the principle, we only believe in the data. That is very scary, also very universal. We say data-driven machine learning technology plus AI algorithm. It's quite scary. Let me go first with the, I'm gonna propose you problem identification typically happening in the experiments. Many people nowadays think about global warming issues, and we are going to produce very important chemical species, for example, hydrogen, oxygen. Here, hydrogen, oxygen came from water split, but there are two ways, of course, thermochemical paths, typical conventional way, and the other very normal way is electrochemical paths. We are going to provide electron or take up electron instead of temperature or heat, thermal energy. But this is quite novel. Why? We don't use any fossil fuel gas here. So environmentally very friendly technology. But anyway, in the classical theory, we know that reactant and product, we want to convert it to other state. Reactant product in daily life, they're stable. Otherwise, we cannot see them. Then we have to convert it. There's always equation barrier. Because we need to change atomic arrangement, also electronic structure arrangement. You chemical bond formation, chemical bond associations. So there is always activation barrier. So classically, people worked on how to reduce the activation barrier. It's quite detrimental factor for facilitating kinetics of the reactions. People thought naturally think about catalyst material. Okay, so experimentally, many people knows that how to design water split. These experimental systems we can think about is the electrochemical pathway, alkaline media or acidic media or combined things. In the acidic media, there's a membrane. In the acidic media, yeah, we can dissociate water, produce hydrogen, or in a cathode and oxygen in the anode membrane. But alkaline media here is better. Why? In acidic media, only platinum is stable. Platinum is the most noble materials. No other metal is more noble than platinum, which means other metal is corroded. Corrosion happens, or dissolution happens. So people try to experiment as they design alkaline aqueous solution media to water electrolyzer, to make water electrolyzer. But here there's no membrane. Electrode, anode, and cathode are exposed to liquid medium. But liquid medium is not vacuum. It is active medium. So another problem came out here. Yeah. How about AEF? Alkaline, yeah, here's the alkaline anion exchange membrane. Sorry, anion exchange membrane. Here is that alkaline media, but we use membrane because we are blocking direct exposition of two electrode liquid media. This is the novel way to do that. Now, Korea government put a lot of money here. AEM, anion exchange membranes, water electrolyze to produce hydrogen and what and oxygen. But the problem I'm going to mention here is this. Platinum is the most, the best catalyst material for any kind of purposes, but it is not in the alkaline media. Actually, platinum in the alkaline media is very bad to produce hydrogen and oxygen. We don't know the reason very well. We did not know very well until I came home. Sorry. And which means that we need a very precise, accurate theory and modeling to describe performance description, for example, catalyst materials. Do we have that one? To do that, we need to understand the exact mechanism from the reactant to product. It involved many different stages, right? And also, eventually, we want to know that material, we have some materials. Can you predict materials and structure? Can you predict the performance? Is there any correlation we can find out, identify? Yeah. Eventually, the experimenters will know that, hey, Bianca, can I design very good catalyst material in working in alkaline media, in the membrane? Can you give me some guideline or design principle? That's what experimenters want to know. Otherwise, theory stuff is very alone. So this is my most of my projects working for this one. Eventually, the calculation theory and model is true to design very good materials. Right? Okay. Also, we can think about Ian mentioned and Alfredo and Urbasek professor mentioned that DFT or molecular dynamics we have to handle with multi-scale. Quantum mechanics only handle with a very small time scale, very small size scale, less than 200 atoms. The reaction time picosecond. But think about material science. It is very big scale, micrometer. Reaction time to diffusion sometimes a second, millisecond. Quantum mechanics, no way to go there. So that is actually bottom line. So we have to never forget that. So in multi-scale nature, we have to think about it, the system design, but we have to understand. We have to understand the mechanism at which levels. This is quite a dramatic, very challenging issue. Let me go over first step by step from the classical theory for heterogeneous catalysis. In the very simple histories, many people involved in that and developing the heterogeneous catalysis theory. But I'm gonna mention two people here. Osterbold and Sabatier. Osterbold catalyst law, he mentioned, of course, he got Nobel Prize. He mentioned that catalysis is driven by thermodynamic law. It is very dramatic, but actually very uncertain. Why? Thermodynamics only care about reactant product, free energy, or entropy. They never think about intermediate. So the main focus on the Osterbold law is that how to proceed, how to change equilibrium constant. That's the main issue. So that's why, as Gurase mentioned, that they are mostly focused on how to change pressure, how to change temperatures, to change equilibrium constant. High equilibrium constant means more product concentration with respect to vacuum constant concentrations. There's most issue they think about. And the other one is that Arrhenius equations. In this case, you know the Arrhenius equation, you plot, the rate constant inverses of temperatures, then you can find out intercept and slope gives you activation energy, and intercept gives you vibration frequency or collision frequency. So do you think about any intermediate in here? No. Arrhenius equation is very widely utilized in experiment, but they don't think about intermediate, which is weighted determining step. No, they can identify. So just use the Arrhenius equation is very silly idea. All right. So again, so they developed a bunch of equations. Of course, got number 5, I think. He calculated equilibrium constant perturbation by temperatures. Only aim is that how to increase equilibrium constant right here, or gives calorimetry equations, gives energy change with respect to temperatures. What equilibrium constant change with respect to pressure? Rosatelier principle, basically. That is the thing, right? And this equation again, this collision frequency and gives the slope gives you activation energy, but there's no intermediate. This is very different from what I'm saying from the Sabatier principle. It is like in catalysis, he's like big guy, I think. Yeah. Sabatier catalyst law mentioned that, here, the catalysis is depend on the stability of intermediate. The first time he proposed intermediate, one of the intermediate has to be the rate determining step. So the catalysis depends on how to unstabilize or stabilize one of the intermediate, which means we can find out optimum intermediate stability. Yeah, this is basically gives you a volcano curve. Yeah, very stable intermediate cannot be easily dissolved. Very weakly absorbed surface, there's no surface reaction. So there's optimum. So for the first time, they say intermediate optimum something. Optimum means what? Engineering terminology. We need to design materials on the aspect of optimization. It's very important concept. Okay, so another theory, right? So I'm going to show that. So here, different from the free energy diagram. See the difference here. This free diagram and this free diagram here. Same free diagram, but here you see that H2O until production of H2, there's intermediate on the surface. So this is first time by mapped by density functional theory in accordance with the Sabatier principle. Now, one of them should be weighted determining step. For example, here, for platinum case, the absorption of H2 on the platinum to dissociate into H and OH is very difficult, very high activation value. You know why? Then you can think about what? The mechanism. Okay? Because of H is very easily absorbed on platinum, but OH is not. Water split only can happen dissociation of H and OH chemical bond. Platinum cannot dissociate OH because it cannot absorb on the surface. This is very different from the post-particle catalyst flow. Also, some other catalysts, right? Optimization, identification, or screening other catalyst materials. One of them is stated to determine step. For example, here you see that the desorption of H and OH on the surface is very much very determined step, or others as well. So we have to think about two things, right? First of all, we have to identify catalyst material which has very strong absorption and OH, and very easily desorption of H on the surface, the optimization problem. Which means that we have to find out catalyst material which has keeps free energy very close to zero. It's very important message we can get from Sabatier principle. So mechanism understanding, what DFT calculation can do for us is that DFT calculation identifying the hydrogen evolution reaction mechanism. As I mentioned that there are two different mechanisms in accordance with the acidic or alkaline media. In alkaline media, as I mentioned that, unlike in acidic solutions, there are a lot of H plus concentration, but alkaline, no. Alkaline case, H source can be only generated by H2O split. But alkaline, remember, H came from split of water, but platinum is very bad. to absorbing which generate substantial amount of potential platinum. Yeah. So DFT calculation can provide us the mechanism. Because again, to generate H source, any catalyst material has to break up this bond, OH and H. Platinum is very bad. Then people can think about which material has very strong OH absorption energy. The first choice is be inhandable even. You can look at handable, which has very high enthalpy formation of hydroxide. That would be the candidate metal. Very simple idea, right? But that mechanism study came from the DFT calculations. Right? That's why the Norskov in Denmark now, he was in the Stanford University trying to postdoc. But he mapped out so famous volcano curve as single descriptor. This is the exchange current density, basically roughly activity of catalyst materials. You see that here, with respect to zero, weak strong absorption and weak absorption of intermediate. The best catalyst material has to be intermediate absorption as of very intermediate. That gives you best one. Still, we can find out volcano here, many room can go. This is a very different scale of the theory. And by using that simple, DFT calculation based on the searching for some metals which has very close explanation near to zero, we can screen many metals or the colloids with a support. This kind of a theory and modeling open new way to design catalyst materials. It's quite a substantial contribution to society. But we can think about catalyst designs. As I mentioned that any catalyst has to four factors. Activity has to be very good. So the activity should be very high, that targeting your purposes, right? And the durability, because catalyst exposed to liquid media, very active or reactive environment. It's not vacuum. DFT calculation, mostly DFT calculation, or performed on vacuum condition. That's bullshit. It's not working in the catalyst area. Catalyst is not working in the vacuum anymore. We are talking about medium, right? So we have to think about activity, selectivity, and durability, and cheaper material than platinum. Yeah, platinum 1 gram, $700. Yeah, give it only to your wife or your husband, not to your other extra. Sorry, I have several extra. Yeah, it's very important. We have many extra. So all right. Also, the structure or environment condition nearby the catalyst. Typical nanoparticle catalyst is not pure; it's alloy, and they are also anchored on the support material. This support can be graphene or oxide or any metal or alumina, whatever. And this total structure is exposed to a reactive environment. DFT can do? No? Almost impossible. Even if you have a quantum computers, I don't think it's possible. Anyway, this is bottom line. Okay. Still we can think about, okay, what DFT can do. Well, here, I mentioned that activity and stability and selectivity durability. DFT can do electrochemical stability predictions. Why? DFT can calculate Fourier diagram, stability of nanoparticle in the acid or alkaline medium. DFT calculation can do nanoparticle. Fourier diagrams in handbook. No information Fourier diagram for nanoparticle. No Fourier diagram for alloy, even binary, there's no information. But DFT calculation can do. Because of this picture, I could be professor in North University. Yeah, you calculate that one. And also another one, right? Molybdenum nickel molybdenum alloy as well. You see here, molybdenum nickels, if you design in alloy systems, the DFT calculation mentioned that, oh no, Kyung-chan, molybdenum easily dissolve it. There's no way to make any alloy with nickel molybdenum surface always, because molybdenum very easily dissolved in alkaline. So this is quite a simple, message, but it's very important message because it provides electrochemical stability, whether you can make a stable alloy in alkaline medium or not. Okay. So now DFT calculation, okay, propose like this scenario. Okay, if you make a molybdenum nickel alloys, molybdenum should dissolve in the alkaline media very quickly. Then what happens? DFT calculation provides, okay, molybdenum dissolvate, but molybdenum oxide can redepart from surface. Surface is going to have very different composition or structure now, with the molybdenum oxide nearby nickel. And the DFT calculation, of course, as I mentioned, that we can calculate charge density difference between pure nickel or nickel to molybdenum or nickel with the molybdenum oxide, which gives you the molybdenum oxide can activate nickel. They change nickel charge density a lot, which is very good for hydrogen evolution reaction. So nickel with molybdenum oxide actually activate nickel. So this is very good catalyst material in the alkaline. But what the DFT calculation could do for us is that they can give us scenario or mechanism. This is a very important message, right? But it is really doable for long time scales. I don't think, no, right? Molybdenum dissolvate, we are not sure 100% molybdenum come back to surface with the oxide. No. As I mentioned before, molybdenum dissolvate in alkaline solutions, there's a membrane. Once molybdenum crosses the membrane, it cannot come back. So this is an irreversible loss of material. So eventually, as time goes on, the catalyst will die. So it's not doable. Okay, so we need something else. With this scenario, we could publish in something, not fertilizer super science, I'm sorry. ACS catalyst. Don't tell how they So another challenge issue I mentioned that, right? Quantum mechanics only has reasons, reaction time and the material size, time and size gap. Yeah, material size is here. There are many ways to bridge between this guy and this guy. There are many mesoscale theory, like a cluster expansion theory, to combine quantum mechanics region and material science region. But I need also cluster expansion theory in MIT, but still I think it's not so much global. Also very difficult for students to understand. So I think a different way is more attractive to students. Okay. All right. That is the data-driven approach. This is very scary. Everyone talking about AI. Everyone talking about machine learning. It is very simply, I can summarize in one slide. Okay. We can measure material property, what we calculate by MD or DFT, whatever theory. We can measure or we can calculate material property. For example, activity, durability, stability, selectivity. We can calculate or measure. Why do we need we don't need the data? Why you get rid of the data? Right? The data is accumulated from the since like 200 years ago. Think about traditional analysis. It starts from 250 years ago. Data is accumulated in the lab. Why do you want to get rid of this data? Anyway, this material property has to connect with something, we say descriptor. Yeah, descriptor, you can easily think about atomic bond, atomic size, atomic bond angle, how many years labor, condition number. It's very micro scale, microscopic descriptor, right? So once you can find out, okay, this descriptor, the correlation between this descriptor or the material properties, very complicated relationship. Should not be linear, almost not linear. Maybe tenth or 100 order of exponential or something polynomials. But here is the scaling point. Data-driven machine learning doesn't care about the equation itself. It doesn't matter 100 order of a polynomial or exponential or cosine, sine. I don't care. They don't care. But they only care this descriptor can describe accurately measured, calculated material property. So there's no principle, no laws. Only I can judge what you say, what you do. I don't care what our friendship know. Only based on the observation of data. This is a very scary point of view. Anyway, once we identify the correlation between the descriptor and material properties, that correlation will be very universal. You can apply to welcome Harry. You missed the most important part, right? So once you identify this one, okay? So most of computational software, computer scientists, they are trying to develop algorithm, how to identify this algorithm very well. in which they don't care about descriptor, they don't care about material properties. They are given. For material scientists, we have no descriptor. What would be the most relevant descriptor based on our know-how or experience or experimental know-how or computational know-how? And what would be the most important material property? For example, catalysis, we have to predict activity, selectivity, durability, and material cost. Very important. So still, I mean, AI, most people are doing AI, they don't care about these two, but actually these two is very important. Otherwise, they are in the random, you know, they are just good at the making script. For what? For doing nothing, right? So we have still camera job. I hear that, right? So algorithm is quite important to, yeah. This is an example. So you wanna predict mechanical property as a Urbas mentioned, diffusion coefficient or decomposition or activation barrier. We can calculate, of course, by NEB technology by using DFT or AIMD. But those kind of material property has to be correlated with the atomistic level. For example, here, right? Certain local environment, coordination number, identity of atom, the charge, the effective charge, on the distance or the angle, whatever. We can locally define specific local environment and try to find out correlation between this information and this material properties. Yeah, using neural network. Most important technology in the machine learning, neural network. Yeah, simulating our brain. Yeah. Very good one is I'm going to show two things. In science point of view, machine learning can do very good two things. The first one is that it can divide into A and B group. Oh, my catalyst, if I design these materials, can it be good or bad? Oh, Byung-Chun, I cannot exactly predict your activity, but I can say it is bad catalyst. It's very important for us, right? And the other one is that, okay, can you really then, okay, I picked up this one. You say this is good, so I made it. Can you predict activity? Of course, this is number. I can predict that. This is quantitative information, qualitative information. It's mostly useful for us by machine learning. Or even I think this is my future goal. Many experimentalists, especially electrochemists, they do measure polarization curve. Voltage or potential as a function of current density. They do measure, but it's actually excited state. It's very difficult to measure. Or computation almost impossible. Why don't we use machine learning to predict polarization curve? So I think it's quite I think doable. Okay. Yeah, neural network, right? You know that AlphaGo, they fit world champion of Go game. But he's Korean, I'm sorry, he's not Chinese, sorry. It's Korean, Isadol. Dol means stone. Isadol. He was defeated by 4-1, but he got win once. This is very important. Nobody care about that, but you see, single game, he used 20 watts of electricity in brain. But Google mind, the machine used 200,000 kilowatts. But nobody mentioned this one, which means that still the algorithm is not very good compared to our brain. So neural network, right? So this is typical neural network in our brains. So we are God's gift, right? So they're very good, but still we are far away. But anyway, the good thing is that the software simulating this neuron is quite advancing very quickly. Also with aid of architectural computer, supercomputer as well. Okay, so typically machine learning, we need the data. I mentioned the data has to be generated or look up from the handbook. Eventually, you're gonna, after refinement, you're gonna make the correlation between this database and material properties. Okay, typically the reference to lookup database is that you know that ICSD, yeah, inorganic crystal structure database. Therefore, 100,000 to 200,000 actually database in there. Crystal structure, yeah, bond angle, melting point, something whatever you can look up it. But my advice at MIT, try to find out something wrong in database. And he became very famous because he found out very wrong database. And he mentioned that there's a lot of errors because some data measured by 90-20, 90-50 or something. Anyway, this is first choice you can do. Well, you can do data mining. You can scan textbook and then the algorithm find out a pattern or something similar word, something that is data mining. Okay? data can generate. Or you see here, this is, I think, most dramatic outcome, successful application of machine learning. In COVID-19, yeah, COVID-19, we tried to develop vaccine, but see, you know that vaccine was commercialized only 62 days. This is amazing. This is first time in the human history. That's because of the Amazon Web Service mentioned that because the machine learning algorithm, they are very good at looking up database from handbook or very good at text mining to find out candidate. Oh, professor, you can design this 10 candidate. Go to lab and design it, made it, and apply it. So they save huge amount of times to develop these ones. So 42 days, I think. In 42 days, they finished collecting the database. Okay. From that, they operate an algorithm. Which kind of combination would be very good vaccine for the COVID-19? So 62 days, 63 days, I'm sorry, they commercialized it. Who got the money? Yeah, the company, right? Yeah. Moderna company, but actually money goes to chemical engineering professor in MIT, Professor Langer. He was co-founder of Moderna. You see, engineering got into knowledge. Yeah. Also, another generated type is that we published 2 papers in Science and Nature, because this paper gives you platinum nanoparticle in the solution phase. Many people thought platinum would be very spherical type of nanoparticle, idealized structures, but actually measure it. We know that the Alibi Santos group in Lawrence Berkeley National Lab, they have a TM, which can measure the nanoparticle in the liquid medium. This is what they measured. When you applied machine learning technology, they much more stable than very idealized structure. So if you used very idealized platinum nanoparticle, probably the reaction or catalysis on the surface may be very misguiding people. So we need a very accurate database to get right answer. Right? This picture also shows that phase transformation of palladium from HCP synthesis apsis. If you design palladium in liquid media within graphene, you can cap up liquid media by graphene. Palladium is grown up into HCP structure, not emphasis. This was not also reported before. Okay, I'm almost finished. Okay, so we also published that one, the catalytic design for some oxygen reduction reactions. This is fuel cell key electrochemical reaction, right? And we could do, because we have a machine learning technology, and we applied ternary compound, platinum carbide and nickel or platinum carbide ions to design very good oxygen reduction reactions. Yeah. And this our result was introduced by science paper. This is one of the future directions we can go. Otherwise, we cannot handle with many multi-element nanoparticles, because it is basically high entropic particles. So DFT is quite not enough to handle with this one. So we have to combine machine learning technology as well. Recently, it is very important topic that single atom catalyst. Yeah. Single atom catalyst is that very good way to save the money, because we can scatter platinum atom by atom. So we need a very small amount of platinum loading, so we can reduce the cost of the material. Yeah. But here another problem. Because the atom is the most unstable quantity in the universe, right? They always want to agglomerate. So we need a very good anchoring support. Okay? Also production of structure on the surface, right? Nowadays also we are working on the single atom catalyst, but not single atom, but different type of metal, like a cobalt, iron, or nickel, but it's scattered in the atom by atom, to design the best materials, right? This paper is just, I think, I'll get email tonight. Okay? I'm happy you accept the submission. I'm expecting this. It's under review in the competition. Nature Publishing Journal Competition Materials. So we did some cooperation with the MIT to develop machine learning technology. But they have very good advanced software skills designing algorithms. Here we found out that single atom cobalt or other metal, we found out that cobalt with other metal, like here zinc or nickel, is much better for bifunctional catalyst. It's a ORR or OER. So it is not really possible with a sizable nanoparticle. We cannot do bifunctional mechanism on the single nanoparticle. Atom by atom, single atom catalyst materials, we can do it. So we identified that mostly cobalt and iron or cobalt nickel, they are very good at ORR and OER if they are scattered out atom by atom on the surface. That's what we found out using DFT calculation and active learning or active machine learning technology. Okay, this is my last slide, as I shown many times before. So the process, for example, in catalyst materials, phase diagrams and surface structure predictions and the catalytic performance and durability and selectivity, whatever, can we predict those kind of material properties by choosing specific alloy element from the pair table. So this kind of process, automated process, we call AI computational platform for catalyst, or for energy storage material, or for energy conversion material, or mechanical something. Yeah, something like that. So in the world, many professors, famous professors, they are designing their own computation platform. Somebody working on catalyst, somebody working on mechanical properties, somebody is working on lithium battery materials. Two big ones, Nomad in Europe, Nomad in the USA, or TIDO project. But big group, right? So this is, I think, the future way to go by simply combine data functional data calculations, machine learning with our expertise and know-how. Thank you very much for listening to my talk and listening my talk. Thank you. Okay, I'm done.
Okay, thank you very much, Richard. Thank you very much, Ian. And thank you very much, Herbert, for these wonderful talks. All of the speakers here are available for questions. If you want to do some questions right now, it's okay. But if you want to contact us, any of us, during the conference, it's okay, anytime. If you have some questions, some students or whatever, or what type of theory can help you. And of course, if you have some ideas from an experimental, give us all the idea. We will make a calculation, and I hope we can find the right answer. Okay, thank you very much for your attention.